Once again, we're looking at the area of the region under the function f of x. So let's draw the continuous function f of x on some interval from a to b, and we're trying to find the area under the curve. As you've seen in the discovery project that we did in class, that the rate of change of area, the derivative of area, gave us function f of x. We're going to assume that antiderivative, the integral of f of x in terms of x, should give us an area back. And now we're looking at the integral on the interval from a to b. You're looking at the precise definition of the definite integral. So we're going to say if we're calculating the sum of the area of the Riemann sums, and as n approaches infinity, the sum of the areas approach the same number. So in this, if this is the case, then we're going to say that function has an integral, and the number the sum approach is called the definite integral. So the expression on the right, you already have seen that it represents the area. So limit with the sigma, it's a summation of infinite number of rectangles. When f of x sub k is the height of the rectangle and delta x sub k is the base. On the left side, you're looking at the same thing. So the sigma is written as an integral. F of x is the function that gives us the height of the rectangle, and dx is the tiny base. We talked about net signed area before, as we're talking about the integral. Since integral is the product of f of x times delta x, so if the function is crossing the x-axis and has positive and negative values on the interval from a to b, so let's say we have a piece with the area a sub 1, we have another piece with the area a sub 2, and we have the third piece with the area as a sub 3, then the integral from a to b of f of x dx will give us a net signed area. So it's going to take an area a sub 1, subtract a sub 2, and add a sub 3. So if we accept the idea that integral represents the area under the curve, then for function f of x, so for continuous function, if function f of x is continuous on some interval from a to b, we should be able to look at certain properties. So we're going to look at 6 of them. So the first one, if I'm going to ask you to find the integral from a to a of function f of x dx. So if we're going to look at the diagram, so we have a function, continuous function f of x on the interval from a to a. So in this case, the delta x, the change of x, is equal to 0. So we should expect that multiplication of the function by the no change in x, or if you look at the line has no area, that in this case the integral is going to be equal to 0. Now the next property is if we have an integral from a to b of f of x dx, and we want to compare it to the integral from b to a of f of x dx. So in first case, if we're going to find delta x is going to be the whole interval from b to a divided by n subintervals. Then in second case, the delta x is going to be the value of a minus b over n. So it's obviously the opposite of each other, so those integrals are going to be equal to each other with just a negative in front. Now for the third one, let's say we have a complicated function. We're looking for the integral from a to b of f of x dx. However, the function consists of two different pieces. It could be something curvy and then a piece of a line which are connected. The function must be connected. So on the interval from a to b, and let's say that happens at some value of c. And if we're looking at the total area, can we expect that the total area is going to be the area of two different pieces? So if we need to find the integral from a to b of f of x dx, we can first find the integral from a to c of f of x dx, and then add the area on the interval from c to b of f of x dx. So as long as c matches, then we can add two integrals. All right, so our next property, let's say I'm looking for the integral from a to b of function f of x dx, and if we look at the diagram, let's say my function f of x is negative. So this is the area of the region from a to b. So f of x is less than 0. So do we expect that the integral, since its net area, will also be less than 0? It's going to be negative. However, if we want to find the area of the region, then we're going to be looking at absolute value of the integral from a to b f of x dx. Now, I can also ask you what's going to be the integral from b to a of f of x dx. Since now the function is negative and the delta x is negative since we're moving backwards, then in this case, the final answer should be positive. Okay, the fifth property is an integral from negative a to a of f of x dx, and the function f of x is an odd function, so let's say something like x cubed. So we're looking at from negative a to a, so we're looking at this piece plus that piece. Now, do you agree, since the function is odd, the negative and positive piece is going to cancel each other, and then the final answer is going to be 0. So we're looking at f of x is an odd function in this case. And the next one, the last one, number 6, we're going to look at the same integral from negative a to a, and in this case, function f of x dx is going to be an even function. So let me sketch the graph, something like a parabola. So from negative a to a, and I'm looking at this piece plus that piece. Here's the 0 in the middle. So in this case, f of x is even. Do you agree that this integral could be written as 2 times integral from 0 to a f of x dx? All right, that's it for notes. So write it down, look at them carefully, come with questions if there are questions, and we'll do examples in class tomorrow.